Today we'll talk about flows again, and we'll talk about weighted flows. We'll talk about what's called minimal cost flow. So this is a weighted version of the maximal flow problem. So in maximal flow problem, we just have to maximize the flow from one point to another point. And all edges are like equal, right? So you just have the capacity and you can push the liquid from here to here, no more than this capacity. And in minimal cost flow, edges are kind of different. So there's different cost of pushing the liquid through each of the edges. So for each edge, we have two parameters, the maximal capacity of the edge and the cost of this edge. So if we have we have two parameters. We'll say CUV is the capacity of the edge. Now, unfortunately, words cost and capacity have the same first letter, so I will use letter W. It's basically like the weight of the edge, right? So if you think about it like a weighted problem, so if you move from bipartite graph to assignment problems, you just get different weights for different edges. So, and if you think about what's called shortest path problem, you can think about the length of the edge or the weight of the edge. So it's just different terminology. So I will use the letter W just for the weight of the edge. So, but I'll usually say the cost of the edge. But I'll use it. So what does mean each edge has a cost? Cost is basically the amount of money you need to pay to push one unit of liquid from here to here. So each unit of liquid which is flowing through this edge costs you WUV money. Yeah. Okay. So what we want to do? We want to build a flow. Let's say we have maximal flow. Let's see. So again, amount of flow is the maximal possible. Flow is just regular flow, yes? So we have a balance in each node except S and T equal to 0, and we want to maximize the amount of liquid flowing from S to T, like in usual maximal flow problem. But for this maximal flow, we want to minimize the cost of this flow. So what is the cost of this flow? Let's say W. W is just total amount of money you need to spend for this flow. How it's calculated is just sum for all edges. So we take sum for all edges, and we just multiply the flow through an edge to the cost of this edge. And for all maximal flows, we want to minimize the total weight of all this. Okay. So we want to minimize the total cost. Cool. So there are different types of these problems. So in some problems, you don't want to maximize the flow. You just want to build some flow of the minimal cost. In some problems, you want to build a flow of a particular size. So we want to build flow of size, let's say X, and from all flows of this of this size, you want to find the cheapest one, right? So there are different variations of this problem. We will consider this variation just for simplicity. Okay, nice. So that's the minimal cost problem, minimal cost flow problem. Okay, let's go. Let's start from the simple cases. Not very simple, but so. The first case is when all costs are non-negative. So let's say that all costs are non-negative. How to solve this problem? Let's start from the simple things. First, let's find the minimal flow of size 0. Minimal flow of size 0 is just the empty flow, right? So F0 is the flow of size 0 with minimal total cost. Yeah? If you want to minimize total cost, you just push nothing. Yeah. So all costs are non-negative. So you just don't do anything, just assign flow for each edge equal to 0, and you will have the flow of the minimal total weight, of the minimal total cost. Yeah. So it's just now let's try to build a flow of size 1. So minimal cost flow of size 1. How to find the minimal cost flow of size 1? Do you have any ideas? How does it look? So you have, again, you have a network, yeah, right? All costs are non-negative. You want to push 1 unit of liquid from S to T. What will the flow look like? Again, what does the flow look like if you take any flow of size 1? How does it look like? Is anyone here? Okay. Just say something. Just need to check that at least somebody's watching. So we have your network, yeah? You want to push 1 unit of liquid from S to T, and you want to minimize the total cost, yeah, of this flow. So what does with me augmenting path? Yes, we want to create one augmenting path. Yeah. So if you have a flow of size 1, it's basically one path. It's not exactly. Again, like we discussed when we talk about network flows, each flow can be decomposed into paths and cycles, right? So if you take any flow of size 1, it is decomposed into one path from S to T, plus some cycles. Yeah. No, any flow can be decomposed into paths and cycles. Yeah. So if you want to take a flow of the minimal cost, we shouldn't take any cycles because each cycle has non-negative cost. So we can take, let's take some flow of the minimal cost. Let's remove all the cycles from this flow. The total cost of this flow will not decrease. Yeah. So actually what we proved that the minimal cost flow of size 1 is basically one path. So if you want to build a flow of minimal cost with size 1, you just need to find a path from S to T. Yeah. And push 1 unit of liquid from this path. Now, if you push 1 unit of liquid using this path, what will be the cost of this flow? The cost of this flow, again, will be just this flow multiplied by the weight of this edge. So the total cost of this path is just the sum of costs of all these edges. And if you want to minimize this cost, you just need to find the shortest path. Yeah? So you want to find the path from S to T with minimal sum of the costs of these edges. So the flow F1 is just the flow which contains only the shortest path from S to T. Okay, now, how to find the shortest path? I want to minimize the total weight for on this path. Yeah? How to find the shortest path? DX algorithm, cool. Okay, let's see. Yeah, I just checked that you're still here. Okay. So we can use Dijkstra algorithm to find the shortest path. Obviously, yeah. So we'll just use Dijkstra algorithm and find the shortest path, and now we know the minimal cost flow of size 1. Nice. Now let's move to the next. How to find flow F2? So again, flow F2 is the minimal cost flow of size. Okay, minimal cost flow of size 2. How to find flow of size 2? Again, what we need to do is to take flow of size 1 and then add one more augmenting path to this flow, right? So if we want to increase the flow by 1, we just need to find some augmenting path and then apply this augmenting path. Just push one unit of liquid through this augmenting path. So to find this flow, we just need to find the augmenting path of the minimal cost. Apply augmenting path of minimal cost to flow F1. Yeah. So we just take flow F1, build the residual network of this flow. In this residual network, we find the augmenting path from S to T with minimal sum. And then using this augmenting path, we increase the flow by 1. Oh, and so on. If you want to move from flow Fk to flow Fk plus 1, yeah, you just take your current flow. Again, the invariant is your current flow is the minimal possible. Flow Fk is the minimal cost flow of size k. Minimal cost of size k, right? So if you want to increase the size of your flow by 1, you just take your current flow, take its residual network, find the shortest path from S to T, then apply this augmenting path and increase your current flow by 1, and so on. Clear enough? Now, how to find this augmenting path for short space? Okay, if you have your current flow and you want to find the shortest path in the augmenting network, in the residual network, how can you do it? How can you find the shortest path in the residual network? Can you do it using Dijkstra algorithm? What do you think? Can you use Dijkstra or not? Why not? That's a good question. There is a small problem here. The problem is that in the residual network, your costs may be negative. How could it happen? What happens when you build a residual network? You have your initial edges. So let's move it here. So you have your edges, yeah, with some capacity and some weight. And in the residual network, you add backward edges. Yeah. So for each edge, you add the reversed edge from V to U with capacity 0. And the weight of this edge, then the cost of this edge, will be minus W. Why is it minus W? Because what does it mean actually to push the flow back from the destination to the source of this edge? It means that if you use this edge in your augmenting path, you basically decrease the flow on your normal edge. Yeah. So again, in your graph, you may have something like this. You may have some edge let's say the capacity, I don't know, 5 and weight 4. Yeah. And now you have some flow through this edge, let's say flow 3. What will happen in your residual network? You will have the edge with residual capacity 5 minus 3 is 2 and weight 4. And you will have the reversed edge. The capacity of the reversed edge will be 3. Yeah. So you can decrease the flow by 3 through this edge. Yeah? And the cost of this edge will be minus 4. Again, what's the idea of these reversed edges? This reversed edge means that you can find some augmenting path like this. So you may have something like this. This is S. Now you use this edge and then go something here. So you may find augmenting path like this. And in this augmenting path, if you use this edge, you basically decrease the initial flow. So if you use this edge, this reverse edge in your augmenting path, you need to decrease this flow from 3 to 2. Yeah? And if you decrease the amount of flow you push through this edge, then the total cost will be decreased. So the cost of pushing 1 unit of liquid from here to here is basically minus 4. So each time you push 1 unit of liquid from here to here, the total cost will be decreased by 4. So even if in the initial network all the costs were non-negative, in the residual network there may be still some negative costs. That's kind of sad, right? So we cannot use Dijkstra here. Okay, how to find shortest path if you have negative edges? So we just find out that we have some negative edges in our graph. What can we do? Can we still find the shortest path? What other algorithms you know about to find shortest path? Bellman-Ford, right? So we can use, even if you have negative costs, you can use Bellman-Ford algorithm here. It is slower than Dijkstra, but it will work at least. Let's build some algorithm. We'll improve it later. Okay. So here in the first iteration we can use Dijkstra. Yeah. But in this iteration, in all other iterations, we have to use Bellman-Ford algorithm because we have negative edges. We will improve it a little bit later. Okay. What will be the total time complexity now? So that's the final algorithm. Yeah. So we start from the empty flow. Then each time we increase the flow by 1. We increase the flow by 1 by finding the shortest possible augmenting path. Each time we find the shortest augmenting path, increase flow by 1, rebuild the residual network, find shortest path, apply it, increase flow by 1, and so on. So what will be the total time complexity? So we make we will find up to f augmenting path. F is the total amount, amount of maximal flow, right? So we find up to f maximal augmenting paths. Each augmenting path we find using this Bellman-Ford algorithm. Bellman-Ford algorithm's time complexity is Mn. So this is the time complexity of the current algorithm. Not great, but not terrible. Okay, nice time complexity. At least something. Now let's try to improve it. How can we improve this time complexity? No, we will improve it by using Dijkstra here. Let's try to do something that will allow us to use Dijkstra in this point. Okay, I just said that you have negative edges in this graph, right? So you cannot use Dijkstra algorithm when you have negative edges. But what if we can modify our graph in such a way that there will be no negative edges? We did it in the previous semester when we talked about Bellman-Ford algorithm and shortest paths. Yeah, maybe you remember if you watched lectures in the previous semester. how can we get rid of all negative edges in our graph? The idea is the following. We can assign some potentials to all the nodes and modify the cost. So we'll assign some values phi v to all nodes of the graph, and we'll change the weight function. So we'll say that the new weight of the edge, vu, uv, uv, okay. So the new weight of the edge will be the old weight of the edge plus the weight of u and the minus, plus the potential of u and minus the potential of v, like this. And the cool thing is this change will not affect shortest paths. So if you take any shortest path in this graph, it will still be shortest path in the modified graph. Again, we discussed it in the previous semester, I just described it briefly. So what happens? If you take any shortest path from S to T, in the initial graph, the cost of this path was just the sum of all weights. Yeah, this is the cost of this path in the initial graph. Now, if you modify the costs like this, what will be the total cost in the modified graph? Total modified will go like this. So it will be sum of all weights plus sum of all changes of potentials. So if you say this is, let's say, V0, V1, and so on, Vk, then these differences will give us something like phi of V1 minus phi of V0 plus phi of V2 minus phi of V1 plus and so on plus phi of Vk minus phi of Vk minus 1, right? No, I just take sum of all these. No, you said I put all these w's in this sum and all these differences into this sum. Yeah. Now in this sum, you may see it right from here that I have plus v1 minus v1, so this will be eliminated, and so on. Everything will be eliminated except this sum and this sum. So the total, so the cost of this path in this modified graph will be something like sum of all weights plus this plus potential of Vk is T and minus potential of V0, which is S. Yeah. So again, if you assign some potential function to all the nodes, just take any numbers here, and then modify the cost of all edges like this. Then the shortest path will still be the shortest path. Why is it true? Because if we take any path from S to T, the cost of this path will be changed by this value. This value is the same for all paths from S to T. So if you change all elements in the set by the same constant, the minimum element will still be the minimal element, right? So the shortest path is still the shortest path. So this constant is the same for all paths from S to T. So, okay, say something. If it's clear enough by now, just say it. It's pretty hard to explain something when you're so quiet. If you have any questions, just ask the questions, okay? Cool. Now, what is it? Now, the next idea. Interesting trick is if you don't have any negative cycles, then you can find the potentials which will make all your edges be non-negative. So there exists this set of potential such that the weight of all edges is non-negative. So if we don't have any negative cycles in our graph, and we don't have any negative cycles in this graph, at any point we don't have any negative cycles. Even in this residual network, we have some negative edges, but we never have negative cycles. Because if you have negative cycles, you can push the liquid through this cycle and decrease the total weight again. So you don't have the negative cycles here. And the point is, if you don't have negative cycles, you can always find the potential which will eliminate all the negative edges in your graph. Yeah. How to find these potentials? Very simple. We just assign the potential of the vertex equal to the distance from S to this node. Let's prove it. Let's prove that if you assign these potentials to the nodes, then all these weights will be non-negative. No, why would they will be non-negative? No, because let's see what's going on. I want to prove that if you take the weight of the edge plus distance from S to U minus distance from S to V, it will be non-negative. Let's push this to the left and just reverse it. So the distance from S to V is no greater than distance from S to U plus weight of the edge UV. Yep. And this is just triangle inequality. It's true. Yeah. So distance to node V is not greater than distance node U plus the weight of the edge, because this is one of the paths to node V, to node U, to node V. So my shortest path is not greater than some path from S to V. So this is true. If I assign potentials like this, then all the weights of all the edges will be non-negative. Cool. But what problem here? What's the problem here? The problem here is to find these potentials, I need to calculate the distances. And to calculate the distances in the graph with negative edges, I still need to run Ford-Bellman algorithm. So basically what I'm doing here, I'm trying to get rid of Ford-Bellman algorithm by finding these potentials. But to find these potentials, I need to run the Ford-Bellman algorithm here. That's kind of sad, right? So, but the cool trick here is that our graph is not changing a bit. So if you just have a graph and you want to run Dijkstra's instead of Ford-Bellman, you need to run Ford-Bellman algorithm. Yeah. But if here my graph is changing only slightly, so I have some small changes in my graph. Maybe if I apply these changes carefully, I will make sure that I will not have any negative edges at any point. What do I mean here? I need to erase something. May I erase this? It's actually not that important. Okay. This is the important part. So I want to apply these potentials, and the potential of the node V is the distance from S to V. Now, what will happen if I find the shortest augmenting path and then apply this shortest augmenting path? Let's look at the shortest augmenting path. So I have this S, and then I have so this is the shortest augmenting path, the shortest path from S to T. What is the modified cost of all these edges? What do you think? So let's take two nodes here. Let's say UV. So modified weight is the initial weight plus distance from S to U and minus distance from S to V. What will it be? So if I take the shortest path, not some path, but shortest path, what is the cost of this edge? What do you think? How do you see it? Okay, let's see. This is the shortest path. Yeah? So this path from S to T is the shortest path from S to T. It means its prefix of this path is also the shortest path. So this part is the shortest path from S to V. Yes? Now, so the length of this path is the distance from S to V. Yeah. Now, length of, again, this part is also a shortest path, right? So the length of this part is distance from S to U. Now, what is the difference between this distance and this distance? It's just the weight of this edge. Again, if you look at the shortest path, then all the edges on the shortest path are critical ones. Yeah. So for each edge in the shortest path, the difference of distances just equals the weight of this edge. Yeah. So the difference between distances of S to V and distance from S to U is just the weight of this edge. Now, if you apply this here, what you will have? By now, it should be quite obvious. So, okay, if I have the shortest path, then for each edge in the shortest path, I have this equality. We will recalculate it right now. So, what will be the modified weight of this edge? We'll just say it, okay? We need to move from here to here. It's easy. Okay, do it. I'll wait. Okay. Okay, we just proved this is true. So, what's this? 0, finally, okay. Okay, so the weight of this edge is 0. Yeah. So if you assign potentials as distance from S to V, then all the edges in the shortest paths are zeros. This actually makes sense, right? No, again, you assign the potential as the distance. If you take the shortest path, and then so the length of this path will be, in the modified graph, will be decreased by the distance. So it must contain all the zeros. Okay. So we have many edges and all costs of these edges are zeros. Now, what will be changed how the residual network will be changed when we apply this shortest path? So when we push one amount of liquid for this path, some edges will be removed from the residual network. Some edges will be added to residual network. If you push one unit of liquid to here, then some of these edges will be removed. Yeah, if the edge was 1, then we decrease the residual capacity by 1, it would become 0 and is removed from the residual network. And some of the edges, like these, will be added, right? Again, if you push liquid here, then that's all what will be changed in the residual network. Some forward edge will be removed, some backward edges will be added. Now, these edges you just added has 0 cost. Because the cost is minus cost of the forward edge. So the cost of all new edges you added to your residual network is 0. 0 is no negative number, luckily. So when we apply this change, all the costs in our graph, in this modified graph, so if we look at on these costs, so all these costs will still be non-negative. And since they are non-negative, we can run Dijkstra algorithm again. So the plan is looks like this. We start from the initial graph. Each time, so again, let's make an algorithm here. So we start from the flow equal to all zeros. Yeah, let's say F. Now each time we want to increase the total flow while there is augmenting path. While there is augmenting path, we run Dijkstra algorithm to find the shortest path. From S. Then we recalculate potentials. Recalculate as distance from S to V. Now in this modified graph, all these costs are non-negative, so we just push one unit of liquid here. All new edges will be zeros, so still we have all costs non-negative. Then we apply shortest augmenting path. Yeah, that's all. That's basically the full algorithm. You just need to implement Dijkstra and that's all. That's all. That's the whole algorithm. You start from this flow of zeros, then each time you find the shortest path using Dijkstra, apply potentials. Now your all costs are zeros. You push one unit of liquid, all new edges are zeros. Now again, all edges are non-negative. So again, you run Dijkstra, find the shortest path, apply new potentials, and push. Then again, run Dijkstra, update your potentials, push one unit of liquid. Again, run Dijkstra, update potentials, and so on. Yeah. That's all. So again, the idea is just that 0 and -0 are both non-negative numbers. That's only true for zeros. Yeah. So for all other edges, you cannot make both these edges present in your graph. It's interesting. Nice. So what's next? Now let's calculate time complexity. Time complexity here is just the same as here, but with Dijkstra. So this you have something like F multiplied by the time complexity of Dijkstra algorithm. So again, if you use Fibonacci heaps, it will be something like M plus N log N for Fibonacci heaps. If you use just regular heaps, it will be something like M log N. If you just use binary heaps, yeah. Okay, it's better than this, obviously. Nice. Now, what happens if you have negative edges? If you have negative edges but don't have any negative cycles? Maybe negative. So if we may have negative edges but we don't have negative cycles. Can we modify our algorithm to work in this case? Yes, yes, yes. We just proved it from the beginning. So basically, when you move from flow of size k to flow of size k plus 1, you need to apply some path plus some cycles. If your all cycles are non-negative, then if you want to minimize what you add, you just need to find the shortest path in the residual network. Yeah. So we just move. So the invariant is that at any point of this algorithm, we have the flow of flow of minimal cost from all flows of this size. So for this size of the flow, we have the flow of the minimal cost. And when we move from one size of the flow to two, when we increment the size of the flow, so we do it by finding the shortest path, because the difference of these flows is the path plus some cycles, and all cycles are non-negative. Yeah. So this is all true if you don't have any negative cycles. Again, now, what if you have negative edges but don't have any negative cycles? What will be the change? What we need to change in this algorithm to make it work for this case? You can run, yes. The idea is very simple. Let's run Ford-Bellman algorithm only once in the beginning to assign the initial potentials. So first, we start from the zero flow. Then when first time we apply Ford-Bellman algorithm, Bellman-Ford find potentials. So we run Bellman-Ford algorithm once, find the potentials, and now we can do the same thing. We can run Dijkstra algorithm all over and over again. You can see in every point we have all costs non-negative. So again, we do the same things while there is augmenting path. We can check it here in Dijkstra algorithm. We can check if we have a path in this Dijkstra. So just to make it more simple, we run Dijkstra, update potentials, and apply augmenting path. Yeah. Now, what will be time complexity? Time complexity would be like this. We run Bellman-Ford algorithm only once, so we need once to run NM to run the first Ford-Bellman, and then F times F times we run Dijkstra algorithm. Let's say M log n. If you use regular heaps, yeah. Nice. Okay, this algorithm is actually good enough for most of the cases you will see in practice, because again, what's the problem here? Problem here is this F actually. This F actually is kind of annoying, because I don't want to have this F in my time complexity, because F is not the size of the graph. F is the size of the flow. Size of the flow can be big, so if size of flow actually depends on the costs you write on these edges. So you can write big numbers on these edges. So even you have small graph, the size of the flow can be pretty big. So this F is not the size of the graph, and I want my complexity to depend on the size of the graph. So it's kind of sad I have this F in my complexity, but in most cases you want to build a maximal flow. In most cases you want to build some small flow. So in most cases. In real problems, you have a graph and the capacities are pretty small. So you have graph of capacities, say 1 or 2. So usually it's not a problem, but sometimes it is a problem. In many problems, this algorithm is good enough. So if you know that your size of your flow is pretty small, it's actually usually good enough to just use this algorithm. It will give you good enough results. Why is optimal short path but same key? It was never better to roll back some paths first. Again, Again, if you want to roll back some paths, it basically means you want to apply some cycle. Okay, let's prove it more carefully. Okay. Okay, let's prove it a little bit more carefully. Let's look at the difference between flow fk and flow fk plus 1. So let's say delta f is the difference between flow of size k plus 1 and the flow of size k. Well, the flow of size k is the minimal cost flow of size k. So fk is the minimal cost flow of size k. Let's look at this difference. The difference of two flows is just the flow in the residual network. So delta f is the flow in the residual network of flow fk. Yeah. So you take flow fk, take it to residual network. Delta f will be a flow in this network. Now, each flow can be decomposed into paths and cycles. So let's decompose this delta f. We'll have some path, one path, right, plus some cycles. All the cycles have non-negative costs because we don't have any negative cycles. So cost of this cycle is non-negative. Now, if we want to find delta f of the minimal cost, so I want to minimize cost of this delta f. Yeah. If I want to minimize the cost of the delta f, I can't take any of these cycles because all cycles are non-negative. So my delta f shouldn't contain any cycles and should contain only one path from S to T. That's why the difference between two consecutive mean cost flows is just one path from S to T in the residual network. Again, this shortest path is not in the initial graph. It's the shortest path in the residual network. So it actually works like this. I'll show you. Let me show you. No, again, let's do something like this. Let's say all capacities are 1. And let's have something like, let's say like, so weights will be, let's see, 1, and I want here, let's see, 3, 3, and 5. Yeah, something like that. And something like 6 here. And all capacities are 1. So capacity of each edge is 1. No, let's do 1. Let's see, capacity is 2, for example. I want capacity of these edges. Okay, let's say capacity of this edge is 1. Just to get rid of it. Let's say capacity is 2. Here capacity is, okay, let's call the capacity is, let's say make it also 1. And this 2. 3. Okay, let's make it 3. So let's look at the following graph. Oh. Don't be rude, please. Now, when you look at the first path, the shortest path is this path. So I find this shortest path. Oh no, it's not shortest path. It's not the shortest path. My bad. I want this to be a shortest path. Yes, I need this cost to be 7, right? Okay, let's have this cost. Yeah, like this. So first number is the capacity, second number is the cost. So the shortest path looks like this. The weight of this path is 1 plus pressure is 7. Yeah. So we push 1 unit of liquid through this path. Here is flow 1, here is flow 1, here is flow 1. Now what happens in the residual network? In the residual network you have something like this. You don't have this edge because the capacity was 1. So now you have the backward edge with capacity 1 and cost minus 1. Here you have forward edge with capacity 2 minus 1 is 1 and 3. And backward edge with capacity 1 and cost minus 3. And you have this edge with capacity 1, 6, and you don't have this edge, you have backward edge 1 minus 3, and this edge. Nice. And now in this graph, you want to find the shortest path. So the shortest path you will find is this path. So you take this edge plus this edge plus this edge. And when you apply this shortest path to your flow, you will have capacity here, or you will have flow here equal to 1. Here you decrease the flow, so it will be 0, and here you have 1. So basically you apply two paths, one path like this, another path like this. And the sum of these two paths will look like this. Yeah, and this is the maximal, or the minimal cost flow of size 2. Something like that. Again, the cost of the first path was 7. Cost of the second path will be 6 minus 3 plus 7. So it is 10. Yeah. So the cost of the next path is 10. So total cost must be 17. Is it true? 8, 14, yeah, 17, right. Okay, I hope it's clear enough by now. Okay, let's move next. Next, what we do if we have a negative cycles? Well, first of all, is it a big problem you have negative cycles? Is the problem even solvable if you have negative cycles? When we talked about shortest path algorithm, we discussed that negative cycles is the big problem for the shortest path problem. Because if you have a negative cycle, then the shortest path is actually minus infinity. Because you go to the shortest path, so you go to this negative cycle, then use this negative cycle infinitely times, and then move to the end. So the weight of the shortest path is minus infinity. Basically, you don't have any shortest path. For any shortest path, you could add the cycle and make even shorter path. So, so if you have negative cycles, then the shortest path problem doesn't make sense. But what happens in the minimal cost flow? Is it even solvable? So, can we use this negative cycle to make the total cost of our flow be minus infinity? Yes, yes. The difference is that the capacities are limited. So yeah, so we cannot make the flow of the minus of the cost minus infinity. the cost of our flow is bounded, has a lower bound. Yeah, so we say that the total cost of our flow is always not greater than the sum of everything. Well, let's say something of everything f multiplied uv multiplied by w uv for all negative edges. So we cannot cannot make this cost of this flow lower than this bound. And since we have a lower bound, we have some minimal value. So the problem makes sense, right? So we have some minimal cost flow. We just need to find it. How we'll find it? We'll do a very simple thing. We will let's find some negative cycle. What can you do if you have a negative cycle? You find some negative cycle. And the sum of weights is less than 0. What can you do it if you have a negative cycle? Well, you can push a unit of liquid through the cycle, you right? So you can increase the flow by 1 using this cycle. Yeah. If you just push 1 unit of liquid through the cycle, you will decrease the total cost. Well, let's do it until we have no negative cycles. So algorithm, very simple algorithm. Let's find any negative cycle and then try to increase the flow through the cycle. It will decrease the total cost of the flow, right? Let's do it until we have no negative cycles anymore. So we try to find any negative cycle, push the liquid through the cycle. Find another negative cycle, push the liquid, and so on. Yeah, it kind of looks weird, and actually, but the problem makes sense actually. Actually, there are a lot of problems which can be described as some problem when you have a maximal flow, not maximal flow, but you need to find flow and you have negative cycles in this problem. It's actually practically just important to solve this problem. But usually what happens, you need to find not the flow in this problem, but you just need to find circulation. So let's just find the flow of size 0. Yeah. Basically, because if you learn how to find the flow of size 0, then you apply all the same technique. So you just have your current flow of size 0 of the minimal cost, and then you apply all these augmenting paths. So basically, the difference is to the first step. So when we try to find the flow of size 0 of minimal cost, that's the only difference from the previous problem. So that's what we're doing. So we'll try to find the flow of size 0 of minimal total cost. Again, how you do it? You find negative cycle, push 1 unit of liquid. Find another negative cycle, push 1 unit of liquid. If you don't have any negative cycles, then you have a flow of minimal cost. Okay, let's say. Let's prove it. If we have no negative cycles in the residual network, if and only if we have maximal flow of this size, minimal cost for this size. For example, in the beginning, if we don't have negative cycles, we have the minimal cost flow of size 0, right? If we just do it in the beginning of the algorithm. Let's prove it. Well, first of all, if we have minimal cost flow, then we don't have any negative cycles. Because if we have a negative cycle, we can push 1 unit of liquid and decrease the cost of the flow. So if we have minimal cost flow, there's definitely no negative cycles in the residual network. Let's from the other side, if we have no negative cycles, let's prove that our current flow is minimal possible. How to find negative cycle? Yes. You can do it using Ford-Bellman algorithm. Use Bellman-Ford algorithm, trying to find shortest path. And then you make one more iteration of the Bellman-Ford algorithm, find the vertex that was changed, and then from it you go backwards until you find the, this typical algorithm. Again, we discussed it in the previous semester. It's just standard algorithm for the graph. Yeah, you can do it using Ford-Bellman algorithm. Right. It's kind of tricky, but nothing that complicated. Again, you just run Bellman-Ford algorithm n iterations instead of n-1. Usually you run n-1 iterations because the shortest path always contains no more than n-1 edges. But you're trying to find shortest path of size of n edges except and then if you find any node which was so the distance to this node was decreased in the last iteration of the Bellman-Ford algorithm, you just go backward from this node until you find the cycle, and this cycle will be a negative cycle. No, it's not that tricky. It's okay. What I want to prove from this to here. So I want to go from here to here. I want to prove that if I don't have any negative cycles, then my flow is actually the minimal cost flow. How we do it? You know, again. Let's see if our cost is not the minimal cost. So we have our cost, our flow, and we have some F2 is the flow of minimal cost, the minimal cost flow. Let's say opt. And the size of this flow is the same. Yep. Now let's look at the difference between these flows. So let's look at the difference between optimal flow and our flow. Again, delta F. So again, the difference of these two flows is just a flow in the residual network. So delta F is a flow of size 0 in residual network of flow F. What is the flow of size 0? Flow of size 0 can be decomposed into set of cycles. Yeah. Usually we decompose flow into set of paths and cycles. But if flow has size 0, it just decomposed in set of cycles. So we decompose into cycles. Now, each cycle has no negative cost. Again, I go from here to here. If I don't have any negative cycles, then each cycle in this decomposition has no negative cost. It means that the cost of this delta F is, so let's see. So the cost of this delta F is non-negative. So it means that the cost of this F opt will be greater or equal than the cost of this cost F. Again, what I want to do, I want to look at the difference between two flows, my flow and the optimal flow. This difference is just some circulation, so it's flow of size 0. We can decompose it into cycles. Each cycle is non-negative, so the difference is non-negative. It means that the optimal flow is not greater than my flow, not less than my flow. Yeah? Ta-da! That's all. So the algorithm works like this. Find negative cycle, push the liquid. Find negative cycle, push the liquid. Very simple algorithm. What's interesting thing is that you actually can get a polynomial time algorithm from this point. So from this algorithm, you can actually build the polynomial time algorithm. It's done like this. You need to push the liquid. You need to use not some negative cycle, not any negative cycle, but to use a good negative cycle. And the idea is to use the negative cycle of the minimal possible average cost. So you find the negative cycle which minimizes the ratio between the sum of all this cost and the number of the edges here. And if you apply this operation not to any negative cycle but to this optimal negative cycle, then the number of these operations will be polynomial of the size of the graph. I will not prove it today, but you can read about it if you're interested. So that's one of the way to build the polynomial time algorithm for this minimal cost problem. Do we have any more time? Oh, we have some more time. Okay, well, let's do a final thing. And the final thing, I want to do something more effective than we just discussed before. So again, the best algorithm we discussed by now. Let's do it here. The best algorithm we discussed by now has time complexity f by this. Let's say if you have a negative by this Dijkstra. Yeah. So the best algorithm we discussed by now is something like this. How to find the optimal negative cycle? Just do it. I don't know the easy way to do it. I know how to do it using binary search plus find a negative cycle. It can be done without binary search, but I'm not sure how. Can you do it? No, you can do it in polynomial time without binary search, obviously, but how to do it fast? I'm not sure about this. This algorithm is polynomial, but it's actually pretty slow. So we actually can do better. Not all polynomial algorithms are practically effective. So in some cases you want to run something which is not exactly polynomial, but is just fast in practice. This is actually one of these cases also. So this algorithm you can construct from this idea will be a polynomial, but it will be just slow. Now, so that was the algorithm we discussed before. So when each time you run Dijkstra algorithm to find the shortest augmenting path. Let's try to get rid of this f. Let's try to get rid of this f. I will do it using the scaling technique. Scaling, again, if you watch the first lecture about maximal flows, scaling is just basically when you try to, how we did it? So we try to find the augmenting path with capacity at least 2 in power of k, then we decrease this k by 1, find another shortest path, and so on. So we just want to use these powers of 2 to find not some shortest path, but some big shortest path, but not some augmenting path, but an augmenting path of a big capacity. And we'll do something similar here. So in the end, we will have in the complexity not this amount of flow, but the logarithm of it. Again, what's the idea? I'm not sure if we discussed it or not. I don't remember. So how can you do a scaling technique? Let's have a graph. Let's have a graph. I explained it to someone not so long time ago. I'm not sure if I explained it to you, but let's just repeat. So let's have some graph with capacities, let's say 3, 5, and 4. Yes. So that's my graph with the capacity of the edges. What I want to do, I want to build this graph from graph with 0 capacities. So what is the idea? I want to start from graph with 0 capacities. And then eventually go to this graph. What operations can I do? I can do two types of operations. I can increase the size of one edge by one. So that is the capacity. So first operation is just take one edge and increase capacity by one. The second operation is to double all capacities of all graph. So I can increase capacity by one, or I can double everything. Now, let's try to build this graph from this graph using minimal number of operations like this. Why do people want to get rid of logarithm of it? No, it's mostly theoretical reasons. So for theoretical computer science, it's like more interesting to discuss algorithms have strongly polynomial time complexity. So it's like more cool for theoretical algorithms than if you have algorithm which has actually a real polynomial time complexity. If you have log f in your time complexity, it's almost linear. It's almost polynomial. But actually depends on what this f is about. So you may, for example, this log f actually implies that, for example, your capacities are integers, usually. And if they're not integers, then you have some fixed number of digits. So this log f is actually number of digits in your numbers, right? And if you have not integers and not real numbers, but something strange, how will it affect your algorithm? So if you can get algorithm with time complexity without all these log f factors, then it actually it's just more interesting for other theoretical results in the computer science, if it makes sense. What I was doing? No. So I want to move from this graph to this graph using only these operations. What is the minimal number of operations you need? Okay, let's start from the simple problem. You have number 0 and you want to go to number 5. Yeah? You can make two types of operations, +1 and multiply by 2. What is the minimal number of operations? How to find the minimal number of operations to go from 0 to 5? Okay, how to get this number 5? To get this number 5, we need to have the previous number equal to 4, right? Because the last operation was +1, so this number was 4. To get this number 4, the previous operation was 3 or 2. So the optimal obviously will be from 2. So we have multiply by 2 here, +1 here. Now to get this 2, the previous number was basically 1. So we can have any one of these operations. Let's have multiply by 2. And now, so this is the optimal way to get number 5. Now we'll just apply the same trick to all elements here. So what's basically happening? So let's look at the binary representation of each number. So number 5 is just 1, 0, 1. 4 is 1, 0, 0. 3 is 0, 1, 1. What I will try to do is to first put these first digits in their places. Then, when I multiply everything by 2, I shift everything to the left. Then I set the next digits, shift everything to the left. Set the next digits, shift everything to the left, and so on. So I will start by putting this first digit. I need to put first digit here and here. So I put 1 and 1 here in 2 operations. Okay? And now I multiply everything by 2. So I will have 2, 0, and 2. Now I need to set the second digit. I need to set second digit only here. So I increase this element by 1. So we have 1, 2, and 2. And then again multiply everything by 2. 2, 4, and 4. Let's make this also. So I increment this element and this. Let's mark it here. I increment this element and this element. And here I incremented only this element. Here I multiply everything by 2. And almost all. Now you need to set the third digit here and here. So I increment these two elements. I got 3 and 5 here. So this is my graph. So I just moved from the 0 graph to my graph using only these operations. So what will be the number of operations? The number of multiplications here will be just logarithm of the size of the, no, it's just the number of digits in the binary representation, right? So it's logarithm of the capacity. So the number of operations, second operations I need is just logarithm, let's just logarithm of C. Yeah. So C is the maximal capacity. So I need to double all the capacities at most the number of, at most the logarithm of the maximal capacity. Let's see max. Now, how many times need I to increment elements by 1? Well, let's see. In each step, in the worst case, I need to increment each element by 1. So I need to increment each edge by 1. So I have log C steps. In each step, I may need to increment all the edges of my graph. So in the worst case, number of operations like this is m multiplied by the number of steps, again, by log C. Now let's do the following. Let's start from this graph. And every time we'll try to find the optimal flow for the current graph. So we have a current graph. Let's try to find the maximal flow of the minimal cost for the current graph. In the initial graph, it's pretty simple. So in this graph, if you want to find the maximal flow of the minimal cost, you just have all zeros. And then we will apply these operations, and each time we will maintain the current optimal flow for a current graph. So we will apply these operations. Each time we will maintain the optimal flow for the current graph. So in the end, we will find the optimal flow for the graph that we need. So we start from this optimal flow, and then we apply these operations. In the end, we will have optimal flow for this graph. Get the idea? Now, how to apply these operations? Well, first of all, if you apply the second operation, that's more simple. Well, again, let's move from here. So for this graph, the optimal flow will be 0, 0, 1. Now, if you want to move from here to here, yeah, if you double all the capacities of your graph, how will the optimal flow be changed? So, how to change the optimal flow if you double all the capacities of your graph? Can you see it? So you have your graph, yeah, and then you double all the capacities. The flow actually will also be doubled, yeah. So you just double all the flows on yours. So multiply everything by 2, and you will still have the optimal flow. So when you move from here to here, you just multiply all the flows by 2, and you have 0, 0, 2. So this step is actually simple. When you multiply the capacities by 2, you multiply the flow by 2, and still you have an optimal flow. Now, this step is interesting. What will happen if you increase the capacity by 1? When you increase the capacity by 1, you put one extra edge in your residual network. So let's see what's going on here. So when you increase the capacity by 1, you have these nodes U and V. Yeah. And when you increase the capacity, if this edge wasn't in the residual network, now it is in the residual network. So you add one more edge to your residual network. Now, I want to maintain the property that my current residual network do not contain any negative cycles. So when I add this edge, I may get some negative cycle. Okay? So in my current, I may invariant, no negative cycles. In residual network. Yeah. So before I added this edge, I had no negative cycles. But when I add this edge, they may have some negative cycles also. There may be some negative cycle like this. How to check if there is a negative cycle which contains this edge? Can you see it? So I'm trying to add this edge, yeah? But if I add this edge and I have negative cycle, that's a problem. So before I add this edge, I will check if it may result some negative cycle. So how to check if there is a negative cycle which contains this edge? It's quite simple. So if you want to find negative cycle which contains this edge, you need to take this edge plus a path from V to U. So you take the shortest path from V to U. If length of the so if the weight of this edge UV plus the length of the shortest path from V to U is less than 0, then you have a negative cycle. Okay, now we have two cases. If this sum is greater than 0, then we have no negative cycle. If adding this edge not result in any negative cycles, we just add this edge to residual network and they are done. So if this is false, we just add this edge and still we don't have any negative cycles. If we don't have any negative cycles, then we have the optimal flow. Now, if we have a negative cycle, let's push one unit of liquid. So the capacity of this edge is 1 because we increased it by 1. So for this edge, capacity equal to 1. So when we try to push 1 unit of liquid through this path, this edge will become saturated and it will be removed from the residual network. So we will remove this edge from the residual network. So we just added this edge and immediately removed it from the residual network. Now again, since we didn't have any negative cycles before, we don't have any negative cycles now. Ta-da! That's all. So again, how to make this operation? So I want to increase the capacity of this edge by 1. I check if it will result in some negative cycles. If not, I just add this edge and that's all. If I'll have some negative cycle, I will find this negative cycle. Actually, I find negative cycle of the minimal cost, yeah, because I take shortest path. I take the minimal cycle of the shortest of the smallest cost. I have shortest path here, and push 1 unit of liquid through this path. And when I push 1 unit of liquid, I will remove this edge. So I still don't have any negative cycles. Ta-da! That's all. That's all. So the cost of this operation is actually finding the shortest path. You can find shortest path using Bellman-Ford algorithm again. Or you can apply potentials and run Dijkstra here again. It's a little bit more tricky. You need to run Dijkstra from here, update the potentials, and then again. It's kind of tricky, but still, you can use Dijkstra to find the shortest path. Using again this potential trick. So what will be the total time complexity? Total time complexity will be like this. we need to make m log c such operations, and each time we run Dijkstra algorithm. So total complexity will be log c multiplied by Dijkstra, multiplied by m, multiplied by, so it will be like m squared multiplied by log n. Something like that. Okay, I think it's good enough for today. There are better algorithms for the minimal cost flows, but I think for today it's good enough. Okay.